Welcome! In this session, we'll dive into problem number 640, solve the equation. This problem challenges us to simplify and solve a linear equation, which is a foundational concept in algebra and programming. Let's explore the problem and break it down step by step. In this problem, we are tasked with solving a linear equation in one variable, represented as a string called equation. This equation contains integers and the variable x, and it is always structured such that the left-hand side, or LHS, and right-hand side, or RHS, are separated by a single equal sign. The terms within each side of the equation can either be an integer, such as 1 or -2, or an integer followed by the variable x, like 3x or -5x. These terms are combined using the plus or dash operators, and there are no spaces within the string. Additionally, the variable x always appears without an exponent and cannot have a coefficient of 0. Our job is to solve this equation, finding the value of x, and return the result in one of three formats. If there is a single solution, we return it as x equals value. If there are infinitely many solutions, we return the string infinite solutions. And if no solution exists, we return no solution. The output for this problem is a string representing the solution to the equation. If the equation has a unique solution, we return the value of x in the format x equals value. If there are infinitely many solutions, we return the string infinite solutions. And if there is no solution, we return the string no solution. Let's look at an example. Suppose the input equation is x plus 5-3 equals x plus 2. The output for this case would be x equals 0, which indicates that x has a unique solution, and its value is 0. To understand why the output is x equals 0 for the equation x plus 5-3 equals x plus 2, let's break it down step by step. First, we simplify both sides of the equation. On the left-hand side, the expression x plus 5(3) simplifies to x plus 2. The right-hand side remains as x plus 2. Next, we subtract x from both sides of the equation to eliminate the variable from one side. This leaves us with the statement 2 equals 2. Since this is a true statement, we can conclude that the equation holds, and the solution to x is 0. Now, consider another example where the input equation is x equals x. The output in this case would be infinite solutions. If we analyze the equation x equals x, we can see why the output is infinite solutions. Simplifying both sides, the left-hand side is simply x, and the right-hand side is also x. Subtracting x from both sides gives us 0 equals 0. This is always true, regardless of the value of x, which means there are infinitely many solutions to the equation. Now, let's look at another example. Suppose the input equation is 2x plus 3 equals 3x2. In this case, the output is x equals 5, indicating that there is a unique solution for x, and its value is 5. To solve the equation 2x plus 3 equals 3x2, we start by simplifying both sides. The left-hand side is already simplified as 2x plus 3, and the right-hand side simplifies to 3x2. Next, we subtract 2x from both sides to isolate the variable x on one side. This gives us 3 equals x2. Then, we add 2 to both sides to solve for x, resulting in 5 equals x. Therefore, the solution is x equals 5. Finally, let's discuss the constraints and edge cases. The input string is always valid, with a length between 3 and 10,000 characters. Edge cases include equations where all terms cancel out, such as x equals x, which results in infinite solutions, or x plus 1 equals x, which leads to no solution. Additionally, equations with large numbers of terms must be handled efficiently to meet performance requirements. To begin solving this problem, we first considered the brute force approach. The idea here is straightforward: break the equation into two parts at the equals sign, then manually parse each side to separate terms involving x from the constant terms. After rearranging the terms to isolate x on one side, we can solve for x by dividing the constant by the coefficient of x. This approach has a time complexity of O(n), where n is the length of the equation string, as we only need a single traversal to parse the terms. However, there are some drawbacks. Manually handling each term, especially when considering edge cases like x equals x or equations with no solution, can make the implementation error-prone. While intuitive, this method lacks robustness for handling all possible scenarios cleanly. A more refined method is the optimized parsing approach, which simplifies the process by leveraging string manipulation and arithmetic. Here, the equation is split into left-hand and right-hand sides, and a helper function is used to parse each side, extracting both the coefficients of x and the constants. Once parsed, the results are combined to isolate x on one side. This approach systematically handles edge cases by applying clear conditions. For example, an equation like 2x equals x simplifies to x equals 0, while x equals x implies infinite solutions, and x plus 1 equals x plus 2 reveals no solution. With a time complexity of O(n), this method is efficient, as it involves parsing each side just once. The key advantage is its cleaner implementation, which separates the parsing logic from the solving logic, making the code easier to debug and maintain. However, it does require additional helper functions and careful bookkeeping of terms. Out of these two methods, the optimized parsing approach is the chosen strategy due to its clarity, systematic handling of edge cases, and efficient O(n) time complexity. While the brute force approach may seem simpler conceptually, it is prone to errors, especially when dealing with complex edge cases. The optimized parsing approach, on the other hand, separates the processes of parsing and solving, making the solution more modular and easier to work with. This method is robust enough to handle all scenarios, including equations with no solution, infinite solutions, or valid numerical results for x. The key insight that made this approach effective is the realization that any linear equation with one variable can be reduced to combining coefficients of x and constants, which significantly simplifies the parsing logic and ensures a structured solution. To summarize, the optimized parsing approach stands out as the best choice for solving this problem due to its efficiency, systematic handling of edge cases, and maintainability. While the brute force method is simpler in concept, it struggles with clarity and robustness during implementation. By splitting the parsing and solving steps, the chosen method ensures correctness and makes the code easier to read and debug. This strategy not only handles all edge cases but also offers a modular and reusable structure, making it the most reliable option for solving linear equations like the one in this problem. To solve a linear equation, the first step is to parse the input. This involves splitting the equation into two components, the left-hand side, or LHS, and the right-hand side, or RHS. The equal sign acts as the delimiter here. For example, in the equation 3x plus 2 is equal to 5x, the LHS becomes 3x plus 2, and the RHS becomes 5x. This separation is important because it allows us to work on each side independently. Next, we need to tokenize each side. This means breaking down the LHS and RHS into individual terms like 3x, plus 2, x, and 5. To do this, we traverse the equation character by character, grouping consecutive digits and variables together while making sure the signs are correctly associated with the terms. This tokenization step simplifies the process of categorizing terms into variables and constants, setting the stage for further processing. After tokenizing the equation, the next step is to categorize the terms. Here, we separate the terms that involve the variable, such as 3x and x, from the constant terms, like plus 2 and 5. To determine the category, we check whether each token contains the variable. If it does, it's classified as a variable term, otherwise, it's classified as a constant. This distinction is critical because it allows us to isolate all variable terms on one side of the equation. Once categorized, we simplify each side of the equation by combining like terms. For instance, if the LHS has 3xx, we combine them to get 2x, and if the RHS has 5 plus 2, we sum them to get 7. This simplification reduces the complexity of the equation and ensures that we're working with the smallest possible number of terms, which makes the upcoming steps more straightforward. With the terms simplified, the next goal is to isolate the variable. This involves moving all terms that contain the variable to one side of the equation and all constants to the other side. For example, if the LHS has 2x and the RHS has 7, we might subtract or add terms across the equal sign until the variable term is alone on one side. It's also helpful to ensure the coefficient of the variable remains positive, as this keeps the calculations simpler. Once the variable is isolated, we solve for it by dividing the constant on the right-hand side by the coefficient of the variable on the left-hand side. For example, if the equation simplifies to 2x equals 8, we divide 8 by 2 to find that x equals 4. If the coefficient turns out to be 0, we need to assess whether the equation has no solution or infinite solutions based on the remaining terms. This step is where we finally determine the value of the variable or identify any inconsistencies. Breaking the equation into tokens is a critical step because it ensures that all operations are performed on well-defined pieces of data. This minimizes the chance of misinterpreting terms, especially in complex equations. Simplification, where we combine like terms, is equally important, as it reduces redundancy and helps avoid errors in later steps. Now, we also need to account for edge cases. For instance, if the equation simplifies to one where the variable terms cancel out but the constants differ, like x plus 1 equals x plus 2, the equation has no solution. Alternatively, if both sides are identical, such as x plus 1 equals x plus 1, the equation has infinite solutions. Finally, if there are no variable terms at all, like 2 is equal to 3, we immediately know the equation is inconsistent. From a data structure perspective, the input equation is stored as a string, tokenized terms are held in a list for easy processing, and a dictionary can optionally be used to store coefficients and constants for efficient summation. These choices make the algorithm both flexible and efficient. The operations used in solving the equation are straightforward but essential. Parsing the equation by splitting it into the left-hand and right-hand sides ensures clarity in subsequent operations. Character traversal during tokenization guarantees that no term is missed, even in complex equations. Summing like terms reduces computational overhead, simplifying the equation as much as possible before solving it. Arithmetic operations like addition, subtraction, and division are then used to isolate and solve for the variable. To enhance efficiency, pre-processing the equation, such as removing extra spaces and standardizing its format, reduces potential parsing errors. Early termination is another optimization, where we identify edge cases such as no solution or infinite solutions before performing unnecessary computations. The algorithm is highly efficient, with a time complexity of O(n), where n is the length of the equation string, since each character is processed only once. Similarly, the space complexity is O(n), as tokenized terms are stored temporarily in a list. These optimizations ensure that the algorithm remains robust and performs well, even for longer equations. Here, we start by defining the solve equation function within the solution class. To help parse the equation, we implement a nested helper function called parse_expression. This function takes a mathematical expression as input and processes it to separate the coefficient of x from the constant values. We initialize variables coef and total to 0 for tracking the coefficient of x and the sum of constants, respectively. A sign variable is used to track whether the current number is positive or negative, and a number variable temporarily stores digits as we parse through the string. The while loop iterates through the expression character by character. For each character, we check if it's a plus or dash to adjust the sign, or if it's a digit, we compute the full number by iterating until we reach a non-digit character. If we encounter x, we determine its coefficient. If no number precedes x, the coefficient is treated as 1 or -1 depending on the sign. At the end, the function returns the coefficient of x and the total constant value. Finally, we split the input equation into the left-hand side and right-hand side using the equal sign to prepare for further processing. Now, we call the parse_expression function on both the left-hand side and right-hand side of the equation to extract their respective coefficients and constants. These are stored in LHS_coef, LHS_total, RHS_coef, and RHS_total. Next, we consolidate the coefficients of x and the constants by subtracting the right-hand side values from the left-hand side values. This gives us x_coef, the combined coefficient of x and constant, the net constant value. We then handle edge cases. If the coefficient of x is 0, there are two possibilities. If the constant is also 0, every value of x satisfies the equation, so we return infinite solutions, otherwise, no solution exists because the equation is inconsistent. If the coefficient of x is non-zero, we solve for x by dividing the constant by the coefficient and returning the result in the format x equals value. This completes the implementation of the function. Here, we begin by defining the solve equation method, which takes an equation as a string input. The equation is split into two parts, the left-hand side and the right-hand side, using the equals sign as the delimiter. These two parts are then passed to a helper method called parseExpression, which will process each side of the equation separately. The results from the left-hand and right-hand sides are stored in integer arrays, where the first element represents the coefficient of x and the second element represents the constant term. Next, we calculate the overall coefficient of x by subtracting the right-hand side's coefficient from the left-hand side's coefficient, and similarly, the overall constant is calculated by subtracting the left-hand side constant from the right-hand side constant. Based on these values, we handle three possible cases. If the coefficient of x is 0 and the constant is also 0, the equation has infinite solutions. If the coefficient of x is 0 but the constant is non-zero, there is no solution. Otherwise, we solve for x by dividing the constant by the coefficient and return the result as a string in the format x equals value. The parse expression method is where we process each side of the equation. We initialize variables to track the coefficient of x, the total constant, the current sign, and a temporary number. The variable hasNumber is used to determine whether we're currently working with a number. We then loop through each character in the expression string, appending a plus at the end to ensure the final term is processed. If the current character is a plus or dash, we check if there's a number being processed. If so, we add it to the total constant, applying the appropriate sign. The sign is then updated based on the current operator. If the character is a digit, we build the number by multiplying the current value of number by 10 and adding the numeric value of the character. If the character is x, we check whether a number was being processed. If not, it means the coefficient of x is implicitly 1, so we add or subtract 1 based on the current sign. Otherwise, we multiply the number by the sign to get the coefficient of x, and then reset the temporary number and hasNumber flag. Finally, the parse expression method returns an integer array containing two values. The first is the coefficient of x, and the second is the total constant. This structure allows us to consolidate the results from both sides of the equation in the solve equation method. By breaking the problem into smaller tasks like parsing and consolidating, we ensure the solution is both modular and easy to follow. This completes the implementation of the equation solver. To solve the equation x plus 5 to 3 plus x equals 6 plus x, 2, we start by splitting it into the left-hand side and right-hand side. Here, the left-hand side, or LHS, is x plus 5 to 3 plus x, and the right-hand side, or RHS, is 6 plus x, 2. Next, we parse the LHS. We initialize variables to track the coefficient of x in the constant terms. Coef starts at 0, total starts at 0, number tracks the current number, and sign starts as 1 for positive. As we process each character, the first x adds 1 to the coefficient since there's no preceding number. The plus sign sets the sign to positive, and 5 adds 5 to the total. The dash sets the sign to negative, and 3 subtracts 3 from the total, leaving us with 2. Finally, the last x adds another 1 to the coefficient, resulting in a total coefficient of 2 for x and a constant total of 2 for the LHS. Now, we parse the RHS, which is 6 plus x, 2. Just like before, we initialize the same variables. The first character, 6, adds 6 to the total. The plus sign keeps the sign positive, and the x adds 1 to the coefficient. The dash sign changes the sign to negative, and 2 subtracts 2 from the total, leaving us with a total constant of 4 and a coefficient of 1 for x. Next, we consolidate the coefficients and constants. The overall coefficient of x is the LHS coefficient minus the RHS coefficient, which gives 2 1 equals 1. The consolidated constant is the RHS total minus the LHS total, which gives 4 2 equals 2. Finally, we solve for x by dividing the constant by the coefficient, resulting in 2/1 equals 2. The solution to this equation is x equals 2. For the equation x equals x, we first split it into the LHS and RHS. The LHS is simply x, and the RHS is also x. Parsing the LHS, we initialize our variables. The single x in the LHS adds 1 to the coefficient, leaving us with an LHS coefficient of 1 and a total constant of 0. Similarly, when we parse the RHS, the single x adds 1 to the coefficient, leaving us with an RHS coefficient of 1 and a total constant of 0. Next, we consolidate the coefficients and constants for x equals x. The overall coefficient of x is the LHS coefficient minus the RHS coefficient, which is 1 1 equals 0. The consolidated constant is the RHS total minus the LHS total, which is 0, 0 equals 0. Since the coefficient of x is 0 and the constant is also 0, this equation has infinite solutions, meaning any value of x satisfies the equation. Therefore, the output is infinite solutions. Moving on to the equation 2x plus 1 equals 2x plus 2, we begin by splitting it into the LHS and RHS. The LHS is 2x plus 1, and the RHS is 2x plus 2. Parsing the LHS, 2x plus 1, we again initialize our variables. The first character, 2, updates the current number to 2. The following x adds 2 asterisk 1 to the coefficient, resulting in a coefficient of 2 for x. The plus sign keeps the sign positive, and 1 adds 1 to the total constant. This leaves us with an LHS coefficient of 2 and an LHS total of 1. Similarly, we parse the RHS, 2x plus 2. The first 2 updates the current number to 2, and the x adds 2 asterisk 1 to the coefficient, resulting in a coefficient of 2 for x. The plus sign keeps the sign positive, and 2 adds 2 to the total constant. This gives an RHS coefficient of 2 and an RHS total of 2. Finally, we consolidate the coefficients and constants for 2x plus 1 equals 2x plus 2. The overall coefficient of x is the LHS coefficient minus the RHS coefficient, which is 2 equals 0. The consolidated constant is the RHS total minus the LHS total, which is 1 equals 1. Since the coefficient of x is 0 but the constant is not 0, this equation has no solution. This means there are no values of x that satisfy the equation, so the output is no solution. To analyze the time complexity of our solution, we start by looking at how the input equation is processed. First, the equation is split into 2 parts, the left-hand side and the right-hand side. This splitting operation takes linear time, or n, where n is the length of the equation string. Next, each part of the equation is parsed using the parse_expression function. This function iterates through every character of the equation, and for any sequence of digits, it loops over those digits but ensures each character is visited only once. This means parsing each side of the equation also takes n time. Finally, once the coefficients and constants are extracted, the algorithm performs simple arithmetic operations to combine the results. These operations, such as subtraction, take constant time, or 1. Combining all these steps, the overall time complexity of the solution is dominated by the parsing of the 2 sides of the equation. Since each parsing step takes n, the total time complexity is n plus n, which simplifies to n. This efficient approach ensures the algorithm processes the input string in a linear number of steps, regardless of its length. Now let's discuss the space complexity. The space usage of our algorithm primarily comes from the memory required to store the input equation and the variables used during the parsing process. First, the input equation is stored as a string, which requires n space, where n is the length of the string. Beyond this, the algorithm uses a few auxiliary variables, such as coef, total, number, and sign, to hold intermediate results during execution. Since the number of variables is fixed and does not grow with the size of the input, these variables require only constant space, or 1. Importantly, the solution does not rely on any additional data structures like arrays, lists, or hash maps, meaning no extra memory is allocated beyond the input string and local variables. As a result, the overall space complexity of the solution is n, due to the input string storage, with the auxiliary space being negligible. This makes the algorithm space efficient, as it avoids unnecessary memory usage. To put everything into perspective, let's compare this optimized solution to a naive or brute force approach. In a brute force method, we might attempt to test all possible values for the variable x to solve the equation. For example, if we test k possible values for x, and for each value, we check the entire equation string, the time complexity would be k*n, where n is the length of the string. This approach is highly inefficient, especially for large inputs, as the number of possible values for x can grow exponentially. In contrast, the optimized solution avoids this inefficiency by directly parsing the equation to extract coefficients and constants, reducing the problem to simple arithmetic operations. This leads to a linear time complexity of n. Whether the input equation is short, average, or very long, the algorithm always processes the equation in linear time. In mathematical terms, the algorithm processes each character of the input string at most once, ensuring that the dominant operation is linear parsing. Since no additional data structures are used, the space complexity remains O(n) for input storage. This combination of O(n), time and space complexity makes the solution both efficient and scalable, even for large inputs. When solving equations, there are several common mistakes to watch out for. First, ignoring edge cases can lead to major issues. For instance, scenarios like empty inputs, equations with no solution such as 2 is equal to 3, or even equations with only a single variable are easy to overlook. Always test your solution against these edge cases to ensure robustness. Another frequent issue is incorrect parsing of the input. It's important to carefully handle how you split and interpret the equation. For example, you might accidentally split at all equals signs instead of just the first one, or mishandle signs like x versus plus x. This can lead to subtle bugs, so double-check your parsing logic. Additionally, don't assume that the variable x will always appear on only one side of the equation. In cases where x appears on both sides, such as 2x plus 3 equals x plus 10, failing to account for this can result in inaccurate solutions. Another tricky area is handling no-solution scenarios. For example, with 2x plus 3 equals 2x plus 5, the constants don't balance, making the equation inconsistent. Validating whether constants cancel out in terms involving x balance is critical. Finally, avoid overcomplicating your solution. Using unnecessary data structures or excessive loops can make your code harder to debug. Stick to simple arithmetic and logic wherever possible to keep your solution clean and efficient. Now, let's focus on insights that are particularly useful in interviews. First, it's crucial to thoroughly understand the problem before diving into code. Interviewers often test your ability to identify edge cases and constraints, so make sure to clarify details like whether the equation will always include the variable x or if constants-only equations are valid. Another key area is optimizing your parsing logic. Efficiently splitting terms, managing signs, and simplifying the equation is at the heart of this problem. Using helper functions can help you keep your code modular and easier to debug. You should also consider trade-offs between different approaches. While brute force methods might be simpler to implement initially, they're often less efficient. Optimized approaches, such as reducing the equation while parsing, can be faster but require careful implementation to avoid errors. Finally, remember that interviews are as much about communication as they are about coding. Clearly explain your thought process, especially how you handle scenarios like one solution, no solution, or infinite solutions. This not only demonstrates your problem-solving skills but also shows the interviewer that you can think critically and methodically. Let's take a look at some related problems and key patterns. The classic problem here is LeetCode 640, which focuses on balancing linear equations. But there are other problems that share related concepts. For instance, LeetCode 20, valid parentheses, is highly relevant when it comes to parsing and validating structured input. Similarly, LeetCode 227, Basic Calculator 2, involves managing operators and precedents, which is closely tied to parsing equations. Another example is LeetCode 150, Evaluate Reverse Polish Notation, which emphasizes expression evaluation, a skill that's useful for parsing and solving equations. Beyond these, there are several key patterns and variations you should be aware of. For example, problems may involve not just one variable linear equations but also quadratic or even multivariable setups. The complexity of inputs can vary as well, with some including extra spaces, tricky signs, or missing terms, so be prepared to handle those edge cases. Additionally, extensions of this problem include tasks like solving systems of equations or working with inequalities. Familiarity with these advanced variations can give you an edge in more challenging interviews. By understanding these related problems and key patterns, you'll build a strong foundation for tackling a wide range of equation-solving challenges. Great work! To wrap up, we solved the linear equation by breaking it down into manageable steps. We highlighted the importance of simplifying the equation and validating edge cases. Thanks for joining. Be sure to subscribe and keep practicing to sharpen your problem-solving skills. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!